Writing an OS in Rust. So the first step in creating our own operating system kernel is to create a Rust executable that does not link to the standard library. This makes it possible to run Rust code in the bare metal without an underlying operating system. This blog is openly developed on GitHub. If you have any problems or questions, please open an issue there. All right. To write an operating system kernel, we need code that does not depend on any operating system features. This means we can't use threads, files, heap memory, the network, random numbers, standard output, or any other features requiring OS abstractions or specific hardware, which makes sense since we're trying to write our own OS and our own drivers. This means we can't use most of the Rust standard library, but there are a lot of Rust features we can use. For example, we can use iterators, closures, pattern matching, option and result, string formatting, and of course the ownership system. These features make it possible to write a kernel in a very expressive, high-level way without worrying about undefined behavior or memory safety. In order to create an OS kernel in Rust, we need to create an executable that can be run without an underlying operating system. Such an executable is often called a freestanding or bare metal executable. This post describes the necessary steps to create a freestanding Rust binary and explains why the steps are needed. If you're just interested in the minimal example, you can jump to the summary. Alright, so disabling the standard library. By default, all Rust crates link to the standard library, which depends on the operating system for features such as threads, files, or networking. It also depends on the C standard library, libc, which closely interacts with OS services. Yeah, that's one of the things of Rust, right? Rust links to libc. So in order to bootstrap Rust, that's what they did. Rewriting all of libc in Rust would, actually people are probably doing that. I wouldn't be surprised. Since our plan is to write an operating system, we cannot use any OS-dependent libraries, so we have to disable the automatic inclusion of the standard library through the no standard attribute. We can start by creating a new cargo application project. The easiest way to do that is through the command line. This specifies we want the 2018 edition. I'm going to see if we can get away with the 2021 edition, right? Because that's our current edition. So cargo new BlogOS. Maybe when this was written, we didn't have. Yeah, so that's all we have. Maybe maybe 2015 didn't have some stuff, or 2018 had this needed stuff, but 2021 should work, right? We'll find out. Cargo toml contains the crate configuration, so we're going to add to the no standard attribute to main. So right now our crate implicitly links the standard library. Let's try to disable this by adding a no standard attribute. So we can do this. Hash bang, no standard. Diablo 3 says Rust can also work with Moozle libc. I'm not familiar with that one. Is that like an alternative to regular libc? Oh, the goal is to write a clean, efficient, and standards conformant libc implementation, I guess, to... oh, now I've lost mine. Here it is. Okay. So, that makes sense. Diablo says it's an alternative that's a lot less bloated. Alpine Linux is famous for using it instead of GNUs. Okay. Yeah, and I wonder, I'm gonna Google now because now I'm curious. Oops, there we go. Libc in Rust. Could a libc implementation be written in Rust? I don't see anything obvious. Oh, well, here's Rust libc. Oh, it's just FFI bindings too. Okay. All right. If I do this, when we try to build it now, the following error occurs. Println doesn't exist, right? Language item required but not found. Personality. Personality. You really need it. Shishak says, hey, you're going to write some OS? I am going to write some OS. Well, I'm going to follow along from the blog post for writing an OS, yeah. Diablo says it's popular with embedded systems due to requiring less support from the OS. Oh, okay. I wonder what Oxide uses then for their, if they use libc for Hubris. Probably not, right? Because this is an operating system written in Rust, but for microcontrollers. So they probably don't have any libc stuff at all. All right. This says error can't find macro println right in the scope, but this also goes on to say, oops, language item not required but not found. Personality. I don't know what EH stands for. I like my interpretation though. Personality. All right. So the reason for this error is that println macro is part of the standard library, which we no longer include. So we can no longer print things. So let's remove the printing and try again with an empty main function. Okay, I can do that. But now we need a panic handler, apparently. It still says this. Oh yeah, okay, we got that here. Okay, so now the compiler is missing a panic handler function and a language item. So let's write a panic implementation here. So we need to use core. Panic info, right? And then we're going to write a panic handler. This is all in main, so I guess we just put it right up here. Okay, just doing a build here. So we still have this personality issue. The panic info parameter contains the file and line where the panic happened and the optional panic message. The function should never return, so it's marked as a diverging function by returning the never type. That says bang here. Somebody commented on one of my YouTube videos when I was doing the editor saying I should have used this for the die function. And they're right, but I didn't know about that. So this is how I learn, right? There's not much we can do in this function for now, so we just loop indefinitely. The EH personality language item. Language items are special functions and types that are required internally by the compiler. For example, copy trait is a language item that tells the compiler which types have copy semantics. When we look at the implementation, we can see it has a special lang equals copy. I have too many tabs. I should start a new. Let's do this. And put the copy thing here. So we can look at that, and then what I can do is I can just move this, oops, big guy off to a different desktop. You do that too. Do that. Okay, I think we're cleaner now. So yeah, so this is the lang equals copy, what they were talking about. Okay. Okay, while providing custom implementations of language items is possible, it should only be done as a last resort. The reason is that language items are highly unstable implementation details and not even type checked, so the compiler doesn't even check if a function has the right argument types. Fortunately, there's a more stable way to fix the above language item error. Each personality language item marks a function that is used for implementing stack unwinding. By default, Rust uses unwinding to run the destructors. Epic Blarg says, bang means go with a bang. That's a good way to read that. By default, Rust uses unwinding to run all the destructors of live stack variables in cause of a panic. This ensures that all used memory is freed and allows the parent thread to catch panic and continue execution. Unwinding, however, is a complicated process and requires some OS-specific libraries. So we don't want to use it for our operating system. So we're going to disable unwinding. So we're going to modify cargo.toml. You know what I should do is I should get this. Well, once it compiles the first time, maybe I'll commit those changes. Cargo.toml. So get rid of that, and we'll just say profile.dev, panic equals abort, and then profile release, same line. This sets a panic strategy to abort for both the dev and the release profile. Now the H personality language should no longer be required. Okay. There, we got a clean build. If we try to compile it now, another error occurs. Requires start lang item. So we didn't get any build errors, but maybe if I say cargo build here. Ah, yes, because I was just running cargo check. So let's, do I have a build? I don't have a build. Not an editor command break. Let's see if I can. Cargo check. I can add a build to a build command somewhere. So it's just in here. Here's cargo run, cargo check, and here I have a break. So this is probably for the debugger, and I don't ever debug. So let's make this cargo build. I don't need to debug. I'm too good for that. All right, so now if I do this, I can say build, and it tries to build and it fails. Okay, good. So the start attribute. One might think that the main function is the first function called when you run a program. However, most languages have a runtime system which is responsible for things such as garbage collection in Java or software threads, e.g. coroutines in Go. This runtime needs to be called before main since it needs to initialize itself. In a typical Rust binary that links to the standard library, execution starts in the C runtime library called CRT0, C runtime 0, which sets up the environment for a C application. This includes creating a stack, placing the arguments in the right registers. The C runtime then invokes the entry point of the Rust runtime, which is marked by the start language item. Rust only has a very minimal runtime, which takes care of some small things, such as setting up stack overflow guards or printing a backtrace on panic. The runtime then finally calls the main function. Our freestanding executable does not have access to the Rust runtime and CRT0, so we need to define our own entry point. Implementing the start language item wouldn't help since it still would require CRT0. Instead, we need to overwrite the CRT0 entry point directly. Oh. Overwriting the entry point. To tell the Rust compiler we don't want to use the normal entry point chain, we need to add the noMain attribute. Okay. You might notice that we removed the main function. Sure, let's do it. The reason is that main doesn't make sense without an underlying runtime that calls it. Instead, we are now overwriting the operating system entry point with our own start function. And we have to no-mangle it. Okay. And this also goes out with a bang. Loop. Writing a lot of loops. So this should check, right? And if I try to build it, oh, we have a whole bunch of things that aren't building. Probably because we need some sort of a linker change. Yeah, main undefined, but that's what the noMain should have done. By using the noMangle attribute, we disable name mangling to ensure that the Rust compiler really outputs a function with the name start. Without the attribute, the compiler would generate some cryptic start symbol to give every function a unique name. The attribute is required because we need to tell the name of the entry point function to the linker in the next step. Okay, yeah. So that's probably what you have to do here to fix this bug, or this compilation error. We also have to mark the function as extern C, right? Tell the compiler that it should use the C calling convention for this function instead of the unspecified Rust calling convention. The reason for naming the function _start is that this is the default entry point name for most systems. The bang return type means that the function is diverging, not allowed to ever return. This is required because the entry point is not called by any function but is invoked directly by the operating system or bootloader. So instead of returning, the entry point should invoke the exit system call of the operating system. In our case, shutting down the machine could be a reasonable action since there's nothing left to do if a freestanding binary returns. For now, we fulfill the requirement by looping endlessly. When we run cargo build now, we get an ugly linker error. The linker is a program that combines the generated code into an executable. Well, it combines the generated code with libraries, right, into an executable. Since the executable format differs between Linux, Windows, and Mac OS, each system has its own linker that throws a different error. The fundamental cause of the errors, you can see I'm using, oh, you can't see. I mean, you can tell from my Apple here that I'm using Apple. Oh, here we go. So I'm using Darwin. To solve the errors, we need to tell the linker that it should not include the C runtime. We can do this. So I guess no standard just means no standard Rust library, but still include the C runtime. We can do this either by passing a certain set of arguments to the linker or by building for a bare metal target. Building for a bare metal target. By default, Rust tries to build an executable that is able to run on your current system environment. For example, if you're on x86-64, Rust tries to build an .exe. To describe different environments, Rust uses a string called a target triple. You can see a target triple for your host system by running rustc version verbose. Sure. So there's the Darwin. LVM 1405. Ooh, this is only 8. And this was written for 135. So I don't know if there's going to be any issues that we're going to run into because we don't have 135. By compiling for a host triple to Rust, compiler and linker assume that there is an underlying operating system, such as Linux or Windows, that use the C runtime by default. To avoid linker errors, we can compile for a different environment with no underlying operating system. An example for such a bare metal environment is the Thumb V7EM None EABIHF target triple, which describes an embedded ARM system. The details are not important. Okay. All that matters is that the target triple has no underlying operating system, which is indicated by the none in the target triple. To be able to compile for this target, we need to add it to Rust up. Okay, none EABIHF. Oh, target add. I left off the add. Okay, that was quick. This downloads a copy of the standard and core library for the system. Now we can build our freestanding executable for this target. Ooh, look at that. So is there a way I can put that in the TOML so I don't have to put a target in there? By passing a target argument, we cross-compile our executable for a bare metal target system. Since the target system has no operating system, the linker does not try to link the C runtime, and our build succeeds without any linker errors. So if I go here, I should be able to see it in the target debug BlogOS. Oh, there's nothing there. Oh, do I have to say thumb? Oh, because that's the target now, not debug. Debug isn't the target anymore. Thumb V7EM is the target. So there's our operating system. It doesn't do much. And it's only 5K, so that's good. Two functions which just loop indefinitely. Plus all the other whatever we need to get that to load, I guess. All right. This is the approach we will use for building our OS kernel. Instead of thumb 7VM none EAB, we will use a custom target, that describes an x86-64 bare metal environment. The details we explained in the next post. All right, instead of compiling for bare metal systems, it's also possible to resolve the linker errors by passing a certain set of arguments to the linker. This isn't the approach that we will use for our kernel, therefore this section is optional and only provided for completeness. Click on linker arguments below to see optional. I'm just going to take a quick peek at it. Oh, okay, so we could do that. Mac OS link args would have to be that, right? Because I guess it adds another underscore on every symbol. And then we have this, and so we have to make it static. Okay. That was an interesting diversion. Let's close that up. So a minimal freestanding Rust binary looks like this. That's what we have. To build a binary, we need to compile for bare metal. Note that this is just a minimal example of a freestanding Rust binary. This binary expects various things. For example, the stack is initialized when start function is called. So for any real use of such a binary, more steps are required. Right? We can't actually do anything yet because we don't have a stack. So the next post explains the steps needed for turning our freestanding binary into a minimal operating system kernel. Okay, let's do that. Let's first commit these changes. Freestanding, BlogOS. Freestanding Rust binary. And I guess I could put this up on GitHub. I'll do that after the stream's over. Okay. I'm guessing we're going to continue with main. All right, so the next post. Let's go back here.